Hey, so we're going to pick up where we left off, which was after we did the first part of example 3, which was we came up with an underestimate for the area under the curve. And again, it was an underestimate because all of the rectangles fell underneath the curve and there were little slivers of that area that were not covered by the rectangles. So what we found here was too small. It should have also included these other pieces right there. All right, so we're on the next page then, and at the top there, and now we're going to do an overestimate of the area. And again, you can see that we're going to be including all these rectangles here. So some of these pieces right here, we're going to include that area, but it's clearly too much because it extends beyond the region that's bounded by the curve. All right, so the answer that we get here is going to be an overestimate. All right, so again, we're going to have those same endpoints that we did before, 2/5, 4/5, 6/5, 8/5, and 10/5. But if you notice that because we're going for the upper bound here, we're trying to get higher than, or we're trying to get to the highest height in each interval, that now we're going to choose the left endpoint, because if we notice that at each left endpoint, that is the highest that we could possibly get. All right, again, you see that it touches the curve right there. Again, in the second rectangle, we're going to this point right here to form a rectangle. In the third one, again, we start on the left. That's our rectangle. And again, that happens because this is a decreasing function. If it were increasing, it would be the opposite way. That in order to form a rectangle with the largest area, we would choose the right endpoint. All right, so it's not always going to be the left endpoint when we're trying to come up with an upper bound. All right, so for part B here, I'm going to say the intervals are the same. But use the left endpoints when evaluating f. Oops, I have a nice new pencil and it keeps knocking into the legs of my tripod here, so sorry if you hear that sound. Okay, so again, just as we did before, in order to find the area of each of these rectangles, we're going to have to find the width of the rectangle and the height of the rectangle. So the width is still going to be the same as before. We're going to take the whole length of 2 and subdivide it into 5 equal parts. All right, so when we figure out what the area is, again, we've got the width. Actually, let me do it in the same order that I did before. We're doing the height times the width. Right, and the width is still going to be 2/5. Again, we're taking the whole length of 2 and dividing it in 5. Right, but now this second part for the height, it's going to be whatever the value of the function is at that left endpoint. All right, so if you remember, before we wanted 2/5, 4/5, 6/5, 8/5, 10/5. Now we want 0, 2/5, 4/5, 6/5, and 8/5. All right, so we have to come up with some way that we end up getting 0 when we plug in 1. Remember, we're going I equals 1 to 5. So we need 0 when we first enter that in. All right, so before it was 2i over 5, but that is, if we plug in 1, we're just going to get 2/5 again. So really what we could think of it is subtracting another 2/5 from that. Let's see if that works. So if we have 2/5 minus 2/5, then that would give us 0. If we have 2 times 2/5 minus 2/5, all right, again, this would be 1 times 2/5 minus 2/5. If we do 2 times 2/5, that's 4/5 minus 2/5. That does give us that second one. If we do 3 times 2/5 minus 2/5, that would give us 6/5 minus 2/5 would give us the 4/5 that we need. So it's the same one that we did before, but each time we're just going to subtract another 2/5. I'm going to write this as 2i minus 2 over 5. Instead of having two separate fractions like that, I'm just going to combine them into a single one. So 2i minus 2 over 5. All right, again, if you need to think about that, just pause for a second, or if you want to go back and watch it again. But I'm taking the same thing that we did before, but because we don't want to start on the right, we want to start on the left, I'm backing it up by 2/5. Okay, so then let's go through with what we did before. So then we've got sigma I equals 1 to 5. And now I'm just going to plug this in to our function. If you remember, it was negative x squared plus 5. So when I plug this in, I'm going to get negative 2i minus 2 over 5 squared plus 5 times 2/5. All right, so this is where we plug that 2i minus 2 over 5 into the function, and then this is still our width. All right, now we're going to use our function, our summation rules that we have, that we talked about at the top of this previous page to split things up. Also on the bottom of this, the first page, which is this one that we could use to split them up. So the first thing I'm going to do is I'm going to take out that 2/5 because that is a constant. So we're going to end up with 2/5 times sigma I equals 1 to 5. And now I'm also going to multiply this out right here instead of, because I don't have a whole lot of room here. So as I multiply this out, I'm going to get a negative, and then this is going to be 4i squared minus 8i plus 4 all over 25. And then I'm going to rewrite this 5 as 125 over 5. Sorry, 125 over 25. Right, just so we can combine it with this now. All right, and when I do that, again, I've still got the 2/5 out front. Sigma I equals 1 to 5 of negative 4i squared minus 8i. And then this is going to be, when this turns to negative 4 and we add it to the 125, we end up with 121 all over 25. Right, we could view this now, this 25 in the denominator there, as a 1/25, which we can then bring out to the front also as a constant multiplier. Right, so when we do that and we bring it out front here, we end up with 2 over 125. And then inside right here, I'm going to take and I'm going to break up the numerator into those three parts. All right, so the negative 4i squared, the minus 8i, and the plus 121. So we're going to end up here with, and I'm going to pull out that negative 4 from the front. So we've got negative 4 sigma I equals 1 to 5 of I squared. Again, see how I took that negative 4 out front right there? Okay, and then I'm going to do the same thing with the second term. So then it's going to be minus 8 sigma I equals 1 to 5 of I. And then plus sigma I equals 1 to 5 of 121. Okay, when I do that then, I've got 2 over 125, right? And then this right here, again, if we go back and we look at, just had it, what I squared is, it's n times n plus 1 times 2n plus 1 over 6. And in our case, see, this was just a general n. In our case, n is 5. So I'm going to fill that in. So again, it's negative 4 times, and then the formula is n, which is 5, times n plus 1, which is 6, times 2n plus 1, which is 11. That's the same thing as we had before in the last problem, over 6, minus 8, sorry, you know what, I forgot to distribute that minus sign through, so this should be plus 8, sorry. Hopefully you noticed that and have been yelling it to me, but I just noticed that right now. Okay, so this should be plus 8 times, and our formula for that one, again, if you look back, is n times n plus 1 over 2. So in this case, it's 5 times 6 over 2, and then plus, and then this is 121 times 5. All right, let me get a little eraser here to make some more room down at the bottom here. Okay, let's keep going then. So as we cancel things out, these two will cancel out. So we'll get 55 times negative 4. All right, so 2 over 125, and then this is 55 times negative 4. I get negative 220. Right, plus this is going to be a 3, so we get 15 times 8. I just did it all on my calculator, so I don't have the computations here, so I'm going to do it for you right now. That's plus 120. And then 121 times 5 is 506, 605. Times 2 over 125, so that should be 2 125ths times 505. Let's just double check that. That is 725, 625, 525, minus another 20 is 505, yeah. And when we multiply this out, we get 8.08. Right? So what we can conclude then is that we can conclude that the area under the curve is less than 8.08. So when we did the first one, we had 6.48, so we know it's greater than 6.48. And now we also know that it's less than 8.08. So the actual area is somewhere between those two numbers. Now, as we go on through the next little blurb here and the next example, example 4, we're going to see how we can come up with the exact value. All right, but before we do that, we need to generalize, because we've just done this for 5 rectangles. But as I said before, we could get a much more accurate answer if we were to allow the number of rectangles to get larger and larger and larger. In fact, if we let them become infinite, then the amount here that is either in excess or not enough here goes to 0, right? Because we keep making smaller and smaller and smaller rectangles, so that little bit that hangs out or the little bit that's not covered will go to 0. And so we need to come up with a property or a way to do that, and we're going to generalize. All right, so we're going to go to upper and lower sums here, and I'm going to ask you for just a second to take and sketch roughly what I have here. You just need 2 matching graphs. I did it ahead of time because I'm not good at doing things similar if I do it on the spot. So take just a second to sketch 2 things like that. So you need a y-axis, an x-axis, an A and a B, and then you need some curve that looks something like that we're going to call F. All right. Okay, so hopefully you have sketches on there that look somewhat like mine. All right, and so what we are going to do, we're considering a plane region, again, that's 2-dimensional, bounded above by the graph of a non-negative function. So again, we're not ready to look at what happens if the curve dips down under the x-axis into the negative territory. So we've got a continuous function, f of x, as shown in figure 4.10, that's this, and we're looking at the region that's bounded below by the x-axis, right? So here's the x-axis right here blocking us off, on the left by the line x equals a, and on the right by the line x equals b. All right, and so what we're going to do is we're going to take, and just like we did before in our exercise example 3, how we took this length of 2 and we divided it into 5 intervals. We want to do this in general. So the first thing we need to do is figure out how long our segment is. So the distance between B and A would be B minus A. And then we're going to cut it into n subintervals. Again, just in general, because we want n to go to infinity so that we get a more accurate idea of what the area, the true area is. And so when we do that, when we take B minus A and divide it by n, that is going to give us the width of each interval, right? And we're going to call that delta x. So if we were to take some interval right in here, and I'm going to try and draw this, let's say right here. All right, we're going to call this delta x. All right, so any rectangle that we draw in here, again, that might not be truly accurate, but just so that you have an idea here, that we're going to make each interval delta x units wide. All right, now as we go through and we call out our endpoints like we did here, we had 0, 2 fifths, 4 fifths, 6 fifths, 8 fifths, 10 fifths. The first thing we're going to do is we're going to start with A, right, because that's our leftmost endpoint, and we're going to add 0 delta x's. Right, and that's just going to that's just going to be our first endpoint right here is A. All right, we're going to note that that is smaller than if we take A and we add 1 delta x to it. We're going to call this value that we get when we take A and add 1 delta x. So again, here's A and we add 0 delta x's. If we add 1 delta x, we're going to end up somewhere over here. We're going to call that endpoint that we get x sub 1. And here we could call this x sub 0. Right, so our first endpoint would be x sub 0, which is A. Then when we add 1 delta x, we get our first x value that we're going to call x sub 1. We're going to note that that's less than if we take A plus 2 delta x's. And again, we're going to call this x sub 2. And we're going to keep doing that same thing until we get A plus n delta x's. All right, that's going to be called x sub n, and that will be the endpoint B. All right, and it's going to end exactly because as we do this, remember, n times delta x, n times this right here would just be B minus A. So if we do B minus A plus A, then we're going to end up with just B. All right, so these will give us the n endpoints that we need. All right, now, this region right here, again, this is what we're trying to find the area of under the curve that's bounded below by the x-intercept, above by the curve, and left and right to the lines x equals a and x equals b. In each interval, there is going to be a point that is the highest point, all right? And we're going to call this f of capital M sub I, right? That's going to be the maximum value. Right, and then there's also a point where it's the lowest in that interval. All right, and we're going to call this f of lowercase m sub I. So in this interval, it's going to have a maximum and minimum, and we know that that exists because f is a continuous function, and the extreme value theorem guarantees that there is a min and a max on each subinterval. Now, it might not be like I've drawn it, where it's at an endpoint of the interval. It could be somewhere in between. But f of lowercase m sub I is the minimum value, and f of capital M sub I is the maximum value in that ith subinterval. All right, this is a lot of detail, so feel free to pause and just ponder for a minute. All right. Next, define an inscribed rectangle lying inside the ith subregion and a circumscribed rectangle extending outside the ith subregion. Right, so again, remember we've talked about this is circumscribed where it goes beyond it, and then inscribed where it stays inside. All right, so it's asking us to do that, to define one that goes above and one that goes below. The height of the ith inscribed rectangle is where f of m sub I would be. right? And the height of the I-th circumscribed rectangle is f of capital M sub I. Again, we just did this in this last exercise right here, all right? So these are our circumscribed ones, and these are our inscribed ones, all right? So you should have that as kind of a very specific example that you have in mind. All right, for each I, the area of the inscribed rectangle is less than or equal to the area of the circumscribed rectangle, right? So area of the inscribed rectangle, again, if we're thinking about our very specific example, the area of our inscribed rectangle, which we're going to call f of lowercase m sub I times delta x. Again, this is the height of the rectangle, and this is the width of the rectangle. So that makes the area when we multiply them together. That area has to be less than the area of the circumscribed rectangle. And again, we're taking the maximum value on that rectangle times the width, and that's going to give us the area of that circumscribed rectangle. So the sum of the areas of all the inscribed rectangles is called the lower sum, and the sum of the areas of all the circumscribed rectangles is called an upper sum. All right, so we've got lower sum, that was like this. And then we've got our upper sum, which is like this, right? And so we're going to call our lower sum lowercase s sub n. It's so difficult to have to keep switching back and forth between lowercase and uppercase. I'm sorry if I forget to say them, but so lowercase s sub n is the sum of all the inscribed rectangles, and then the upper sum capital S sub n is the sum of all the circumscribed rectangles. Right? And so it says from figure 4.12, you can see that the lower sum, lowercase s sub n, is less than or equal to the upper sum, capital S sub n, and the actual area lies somewhere in between there. Right? So we're just saying what we said with that specific example in 3. All right. Not really anything that we need to write on that page, so that was a quick one. But let's take a look now and see how we can apply that in example 4. All right, so we're going to do this, and we are going to just, instead of doing it for, let's say, 5 or 10 or something like that, we're going to just try and generalize this. All right. So find the upper and lower sums for the region bounded by the graph of f of x equals x squared and the x-axis. All right, so this is the bottom, this is the top up here, and it wants to be bounded between 0 and 2. All right, so we need to find the upper sum. All right, that is going to be this one right here. And then the lower sum, which is going to be this one right here. Sorry, I think I pointed to that for the upper sum and you couldn't see it. So that's the upper sum and that's the lower sum for the region bounded by the graph of f of x equals x squared. All right, so we are going to begin. So begin by dividing 0, 2 into n subintervals. Again, our picture makes it look like it's divided into 4, but we're just doing that just because we need a visual here. But we are going to divide it into n subintervals. So if you remember what it said back here just a second ago, that when we want to divide something into n subintervals, we find the length of the interval and divide it by n. So in this case, since it tells us to stop at 2, we're going to end up with delta x equals 2 minus 0 over n, right? Again, this is b minus a, so 2 minus 0, which is equal to 2 over n. So this is delta x, all right? That is the width of each of the rectangles that we're creating. All right, now we need to think about this. If we're doing it at a lower sum, right, do we need the left or the right endpoints? Right, so again, we're trying to get this picture right here. So is the left or the right endpoint of each interval going to give us the inscribed rectangle? All right, hopefully you're saying it's the left one, it's the left, and you would be correct, because notice how in every rectangle that's drawn, we want the left point right here. That is where it's going to hit the curve and be the lowest. Now again, that's opposite of what happened in the last example we did, because the last example was decreasing. And there we took the right endpoint. So it will change depending on whether the function is increasing or decreasing. All right, so in order to get our endpoints, we're going to take our beginning endpoint, which is, remember, here we said we're going to take A, which in this case is 0. So we're going to take 0. So let's just call this our left endpoints. It's going to be 0 plus, and then we want to include the left one. So here the first one we want is 0, and then we would get, again, this is going to be how, we have no idea what this number is, so let's just say this was, I don't know, 5 again. So then we want 0, and then 2/5 and 4/5 and so on. We want the left one, so we want 0 plus, I'm just going to write this, we want it 1 less than whatever counter we're on, times 2 over n. All right, so again, here is our left endpoint, and then as we keep going up, this is how long each interval is, and so, but we want 1 less because we're going to be on the left. So if we just said I times 2n times 2 over n, we would end up with the right endpoint. So we're doing 1 less than that, so we actually get the left endpoint. Again, think about that just for a second. If you did I times 2 over n, then as we went from 1 to n, our first one would be 1, which would give us 2n, and that's to the right. We want to end up at 0 the first time. So if we put in 1 here, we get 1 minus 0, which is 0 plus that 0, so we're going to end up at 0. Okay, so if we multiply that out, we get 2 times I minus 1 over n. So this is the set of all our left endpoints. All right, and again, this is the value of A that corresponds in the example that we just did, or in this right here. That's the A that we were talking about when we did that. All right, so our lowercase s sub n is going to be the sum from I equals 1 to n. And then we need, again, the height times the width in order to find the area, because we're going to be adding up all these rectangles. So the width is 2 over n. And then the left endpoints are here, and so we need to find the value of the function there. So it's f of 2 times I minus 1 over n. Right? So this is the x value that we need to plug in here to find out what the height of the rectangle is. Right, think about that for just a second. Okay. I equals 1 to n. And now we need to plug this into the function. So I'm going to take this and I'm going to plug it into x squared, and so we're going to end up with 2 times I minus 1 over n squared times 2 over n. Right, so now this is telling me I need to find the value of the function at this point, and by plugging it in here, I just did find the value of the function at that point, and still multiplying it by 2 over n. Okay, let's start to clean this up a little bit. So now we've got sigma I equals 1 to n. Let's multiply this out. So if I distribute that, actually, I'm going to not distribute that 2 right in there because it's going to become a constant that we multiply by. So I'm just going to square it. So I'm going to get 4, and then let me square the top. So this is going to be I squared minus 2i plus 1. And in the bottom, I'm going to get n squared. And then I still have this 2 over n. Right? Now, I'm going to combine the n's in the bottom, and then I'm going to combine that 4 and the 2. So I equals 1 to n of 8 over I squared minus 2i plus 1 over n cubed. Right, again, just combine the bottom and multiply the 2 times the 4. All right, now I'm going to take that 8 over n cubed, and again, n is some number, all right? So we just don't know what it is, but it is behaving like a constant. The variable, the thing that changes, is going to be that I, because it's going to keep going through all the numbers between 1 and n. So this 8 over n cubed can come out front as a constant. So this is going to be 8 over n cubed. And then I'm going to break these 3 apart. So we end up with sigma I squared from I equals 1 to n minus, let me bring that 2 out front, sigma I equals 1 to n of I, and then plus sigma I equals 1 to n of 1. All right, now, if you think back to the formulas that we were using, then right here, I've got this constant one that I need, I've got an I one, and I've got an I squared one that I need to use. So I'm going to fill those in, but remember before when this was 5, we were able to just fill it out and get a number. It was really sweet, but we will not be able to do that here. So this is going to give us 8 over n cubed times n plus 1 times 2n plus 1 over 6 minus 2 times n plus 1 over 2. And then the last one is plus n. Again, our constant times our number up there. All right, these 2's are going to cancel out. This part is really annoying, and you're just going to have to trust me on this one, because these, when they multiply it out, always multiplies out to the same thing, and then I'm going to combine it with this n squared plus n plus another n, so we're going to have n squared plus 2n over 6, no, 6 times n squared plus 2n over 6. All right, so this is going to end up being 6 times n squared plus n over 6, which we're then going to combine with this right here. And when we do that, I dropped that and made that a squared. It should be cubed. This ends up being 2n cubed minus 3n squared plus n all over 6. If you don't like that and you want to stop the video and multiply it out and just verify that you get that, please feel free to. I just don't know that it's worth our time for me to multiply all that out right now. All right, so when I can simplify here, I've got an n in each of these that's going to cancel out with this n right here, and then I've also got 2 that's going to cancel in here. And when I do that, I end up with 8 over 3. Actually, I'm going to distribute this through. So I end up getting 8 over 3 after all my canceling, minus 4 over n plus 4 over 3n squared. All right. So again, this comes from distributing the 8 over n cubed to each of these terms. 2n cubed over 6 minus 3n squared over 6 plus n over 6. Distribute that through, and that's what you get. This is our lower sum. Okay, hopefully. Okay, I was just getting ready to say that's our lower sum and it cut me off. So, so now we've got to do this again, but now we need to do it for the upper sum. All right, so I'm just going to do the same thing that we did. Hopefully this second one is going to seem a little bit easier too now that we've already done it once. So again, we need to start by dividing this region that is, wow, I just realized I spelled that wrong, dividing. We're going to separate this, all right, so again, we're going to do the same thing. Delta x is 2 minus 0, or b minus a, over n. So each rectangle is going to be of length 2 over n, but now we need to use the right endpoints. So again, if you think back to what we did here to get the left endpoints, that we started at 0, which we're still going to do, But now instead of knocking back one to get the left endpoint, we're just going to leave it at just plain old I to get the right endpoint. Right, again, if we've got to go to the left, we need to back up, which is what that minus 1 was for. But here we don't need to do that, so this is just going to be I times 2 over n. And so when we want to talk about the right endpoints, it's just 2I over n. That should make our multiplying a little bit easier as we go through to do this. All right, so then we want to find upper S sub n. And so again, we need to find sigma I equals 1 to n. And again, this is going to be the height times the width. And our width is still delta x, which is 2 over n. And then our height is going to be f of 2I over n. Again, the endpoints that we're talking about. So the height at that endpoint. So that's why we've got the f of 2I over n. All right. So again, if we go back to here, think what did we do next? We plugged that into our original function. And so that's what we're going to do here. We're going to have sigma I equals 1 to n of, we're plugging this into x squared. So we're going to get 2I over n squared times 2 over n. This is where I'm saying it's going to be a little bit easier because we don't have a binomial. So this is going to just be I equals 1 to n of 4I squared over n squared times 2 over n. And then that ends up being I equals 1 to n of 8I squared over n cubed. Right? And again, just like we did last time, once we had that 8 over n cubed, we pulled that out in front as a constant. And so that's what we're going to do here. We're going to treat this like a constant, and then we're just going to have 8 over n cubed sigma I equals 1 to n of I squared. This one is so much easier than the last one. It's good we got the hard one done first. All right, so then again, we replace I squared with what we have on our formula. Again, you're going to start to memorize these because you're using them so much, but this is going to end up being 8 over n cubed times n plus 1 times 2n plus 1 all over 6. All right, and when we multiply this out, again, this is going to be something that's probably worth memorizing, that when we multiply this out, 8 over n cubed, this is slightly different from what we had last time. Yes, we end up with 2n cubed plus 3n squared plus n over 6. Last time we had a minus 3n squared in here. All right. Then when we multiply this through and we distribute, all right, I'm going to cancel this. I'll show a little bit more work this time because I can. All right, and then so we've got 4 over n cubed times this, and now I'm just going to distribute that through. And so when we do that, we end up getting 8 over 3 plus 4 over n plus 4 over 3n squared. All right, again, these two n cubes are going to cancel out, so I'm just going to be left with 4 times 2, which is n, and then this 3. When I do 4 times 3 over 3, the 3's cancel and I just get the 4, and then I just have an n left in the denominator, and then again when I multiply through by 4 over n cubed, the 4 and the 3 stay, one of the n's cancels out, so that's why I end up with an n squared in the denominator. And this is my upper sum. All right, so I've got my lower sum. Again, this is very, very general because we don't know what value of n we're going to use. Again, this is also very, very general because I don't know what n value I'm going to use. Notice how similar they are, though. The only difference is that they have the same exact terms, but just this has a minus here and this has a plus. All right, so let's finish this up. Note that lower s sub n is 8/3 minus 4 over n plus 4 over 3n squared, and that is less than 8 over 3 plus 4 over n plus 4 over 3n squared, which is capital S sub n. Now, if we were to take the limit as n approaches infinity, again, this is going to start bringing you back to limits from our first chapter, as we let n go to infinity. All right, so if we take and we let limit as n approaches infinity of our lower sum, which is s sub n, in other words, the limit as n approaches infinity of this, 8/3 minus 4 over n plus 4 over 3n squared, we get 8/3. Right. As n approaches infinity in this term, that term's going to go to 0. That's from what we were just doing in section 3.5, I think. And then same thing here. If we let n go to infinity, this is also going to go to 0, so we just end up with 8/3. If I do the same thing, limit as n approaches infinity of the upper sum, then I get limit as n approaches infinity of 8/3 plus 4 over n plus 4/3 n squared, or 4 over 3n squared. As I let n go to infinity, this goes to 0, this goes to 0, and I end up with 8/3. Right. What that means is that the true area under the curve, since the lower bound is 8/3 and the upper bound is 8/3 and they match, then this is the exact area under the curve. All right, so let's see if we can write a little note there. The exact area bounded by the curve, bounded by x squared, y equals 0, x equals 0, and x equals 2 is 8/3. All right. Okay, that's all I got for you right now. Bye.